Scientists just discovered Voyager still sends a signal from 24,000 kilometers away, but its transmitter runs on just 23 watts, and that contradiction sounds like a nightlight shouting across interstellar space. And it's dying faster than its remaining power can support, but it still whispers home across 23 hours of one-way light time, which means every answer arrives almost a day late and still feels miraculous. Every bit we catch starts as a flicker from a spacecraft that launches in 1977, and that flicker keeps crossing a region that looks like day on paper but behaves like night in every practical way. So if the signal survives this long, what exactly does Voyager hear in total darkness that makes 2026 engineers stop treating the void as empty? According to the inverse square law, sunlight never stops, but distance dilutes it until sunlit becomes a technicality. However, spacecraft don't run on technicalities. Near Earth, the sun hits you with about 1,361 W metis, but out near 160 AU that drops to roughly 0.05 W menus, and suddenly daylight can't pay your energy bills. That's like trying to charge your phone with a flashlight, but the flashlight sits on the moon, and the charging cable is just your optimism. Here's the crazy part. Your own warm skin radiates more power per square meter than the sun delivers out there. So a human silhouette outshines the star that built the solar system. Voyager doesn't die because it can't see the sun, but because the sun becomes too poor to matter. So what does darkness even mean when the real threat is energy starvation? For 6 months, a tiny JPL telecom and heliophysics team hunts a weird pattern hiding inside Voyager's faint telemetry, but every easy explanation breaks in a different way. They blame the Deep Space Network, but the signature repeats across different tracking passes and station timing like it refuses to be a ground artifact. They blame instrument noise, however the pattern stays locked to the same sky direction while the spacecraft keeps moving at about 17 kilometers yes, and noise doesn't care where you point. They try to bury it under aging hardware, but the timing keeps snapping into place like a puzzle piece that wants attention. Then they look at the data one last time, and the noise lines up like a message that arrives from nowhere. So what could possibly repeat in the dark strongly enough to survive a 24 billion kilometer whisper? The reveal hits like a punch because it turns emptiness into something you can almost feel. Voyager doesn't see nothing. It hears space. The plasma wave instrument turns charged particle oscillations into an audible signature, and a narrow tone near 2,600 Hz starts appearing at just the wrong moments. 3 details lock the team's breathing into the same rhythm. The tone pops up as a thin, stubborn line in the spectrogram instead of a smeared hiss. A matching jump appears in measured plasma conditions at the same time, and the magnetometer shows a twitch that arrives within about 90 seconds of the tone, like the boundary itself flinches. Here's the crazy part. The implied electron density points to around 0.05 electrons per cubic centimeter, but the region sits far beyond the sun's familiar wind, where you expect the environment to smooth out, not get more structured. So, if the interstellar medium should feel like calm fog, why does Voyager hear a clean note as if something plucks a cosmic string? But here's what breaks them. The tone doesn't behave like a smooth background. It arrives in sharp steps, like Voyager crosses invisible ribs in space. However, standard models treat this boundary as a gradual fade from solar influence to interstellar flow. The team stares at their own assumptions and realizes the story they tell in textbooks sounds too neat for what the data insists on. The heliosphere stops acting like a simple bubble and starts acting like layered material, like sheets stacked and folded, and Voyager threads through them like a needle. If those layers stay real, a fundamental assumption inside the models starts wobbling. The idea that space plasmas behave like smooth, ideal fluids at the edge of the sun's domain. So what shapes the boundary into ribs, dust, magnetic seams, turbulence, or something we haven't named yet? The implications land immediately because structure at the boundary doesn't stay philosophical. First, deep space crews face radiation weather that shifts faster than planning likes, but mission roadmaps still rely on average shielding assumptions that pretend the sun's shield behaves politely. Second, future interstellar probes fail on power if they depend on sunlight. because out here the sun delivers only 0.05 WM2s. However, instruments demand watts the way lungs demand oxygen. Third, inside NASA, a boundary hazard review meeting gets called because comms, navigation, and crew dose margins all hinge on whether the heliosphere protects consistently or flickers like a torn sail. If Voyager's darkness contains ribs, then the solar system's edge isn't a line you cross once, it's a terrain you traverse. So what happens when a crewed mission meets a bad weather rib at the wrong time? Not everyone accepts a clean tone in deep space without a fight, and the skepticism arrives sharp because the claim sounds too cinematic. Dr. Elaine Park at the fictional Interstellar Plasma Group says, "A clean tone in deep space usually means your hardware sings, not the universe." But the team cross-checks timing across independent subsystems, and the tone keeps landing where the physics says it should, rather than where the engineering would accidentally place it. They swap assumptions, rerun clock models, compare DSN past conditions, and the line keeps surviving like it's pinned to the boundary itself. However, skepticism doesn't die. It evolves into a nastier question. If Voyager's hardware doesn't sing, what in interstellar space plays a 2600 Hz note on command? Then one signal refuses to fit even the ribs story, and it feels like a knock inside the knock. At exactly 02:17:43 UTC, the downlink carrier shows a tiny phase. Tick, the tone brightens, and the plasma counter spikes. Then everything calms down like someone taps the glass and walks away. The tick repeats only a few times, but it clusters near the same boundary-crossing moments. However, coincidence loves to impersonate meaning when humans want patterns. The team tags every tick against tracking handoffs, pointing history, and thermal cycles, and the excuses keep collapsing until only one uncomfortable overlap stays bright. The tick likes the boundary. So what touches a spacecraft in the dark? Dust grains, magnetic reconnection, a filament of plasma, or something stranger that only exists at the edge of the sun's influence? The loneliness of Voyager stops being poetic and starts being mechanical, because the spacecraft survives on a shrinking budget of heat. Voyager runs on plutonium power, but decay squeezes the mission like a closing fist. Pew 238 carries an 87.7-year half-life, so the available watts fall predictably. However, the spacecraft can't half-run a heater or kinda support a transmitter. It either does or it doesn't. Every shutdown saves power, but every shutdown also changes temperatures, electrical noise, and timing, which can fake patterns if you aren't ruthless about controls. That's why the team's next step matters. They need a test that punishes the spacecraft but doesn't punish the sky. So how do you prove the 2600 Hz tone comes from space and not from a starving machine slowly changing its own voice? Voyager's communication link makes the whole drama possible, but it also turns every clue into a fragile artifact you can lose. The signal crawls home at tiny data rates, but Earth tracks it with ridiculous precision, using DSN 70-meter dishes that dig whispers out of static. However, the link fights fading power margins, plasma distortion, and sheer distance every day, and one tiny tracking change can decide whether the next tone packet decodes cleanly or arrives half-corrupted. That makes every downlink feel like roulette with physics as the dealer. So if the next packet arrives damaged, how do you separate a real interstellar tone from a broken one without lying to yourself? Here's the crazy part. Voyager can't take a photo of interstellar space, but it can listen to charged particles vibrating, and frequency becomes a ruler. When the tone sits near 2600 Hz, the density math points toward about 0.05 ECEM3, but the boundary should smear, not step, if it behaves like a simple fluid. The team overlays the tone moments against where Voyager sits relative to known transitions, and the map starts to feel like a story the sun never tells in bright inner space. Voyager crosses the termination shock around 94 AU, then reaches the heliopause around 121 AU, but the surprising layered structure appears farther out, as if the edge itself has an extended anatomy. Layers imply history. Something pushes, something folds, something locks, and locked structure implies a mechanism that repeats. So what event folds the heliosphere's edge into ribs instead of one clean wall? Now the suspects step forward, and each one sounds plausible until you force it to explain sharp steps without cheating. Suspect 1. Dust grains form a thin sheet, but dust usually blurs gradually. However, a magnet-aligned dust sheet can cut like a plane if the geometry stays coherent. Suspect 2. Magnetic reconnection forms a seam, but seams should move when solar pressure changes, and Voyager sees steps that look stubbornly anchored. Suspect 3. Turbulence stacks into ribs, but turbulence usually looks messy, so why does it look organized enough to produce repeatable tones? The universe doesn't hand you a neat list of suspects, but Voyager's data does, and that list feels like a dare. So what single measurement eliminates two suspects immediately and leaves one standing in the dark? The team tightens the trap with the only thing that consistently kills illusions: controlled comparison. They line up DSN passes, rule out receiver quirks, check clock behavior, and the 2600 Hz line stays pinned to physical boundary moments rather than Earth-side schedules. Then the Zero Tube's 17-day 43 UTC tick shows up again in a different pass and lands like a fingerprint on glass, and fingerprints don't happen when nothing touches anything. But here's what makes it cruel. Every time you chase the tick, you spend power, and every watt you spend now steals tomorrow. So if you sit in mission control, do you spend the last clean hours hunting the tick's source, or do you spend them mapping the ribs that make the tick meaningful? That dilemma becomes more than a romance with mystery in 2026, because modern mission design pushes humans and hardware deeper into radiation risk environments, and Voyager quietly argues the sun's shield doesn't behave like a smooth umbrella. A layered boundary implies variable cosmic ray filtering, and that changes electronics risk, comm reliability, and crew dose margins in ways that don't show up in pretty averages. However, planning hates variable, because variable turns schedules into guesses, and guesses turn into headlines. If Voyager reveals weather at the edge, what tool gives the first true forecast before a crewed mission rolls the dice? This is where the 2026 news cycle starts to matter, but not in the way people expect. ESA's Plato targets a 2026 launch window with ultra-stable detectors, and that stability forces calibration techniques so strict that other teams steal the philosophy immediately. Better calibration can separate space signal from instrument song, but here's the crazy part. It can also reveal fainter patterns already buried in Voyager's noise floor by shrinking error bars until excuses run out. Tight error bars turn maybe into no escape. And if the rib pattern survives better calibration discipline, it graduates from mystery to map feature. So if the ribs stay real under harsher scrutiny, what physical process locks them into place across billions of kilometers? Dr. Kenji Alvarez, a fictional heliophysics lead, says, "An edge that stays put while the spacecraft changes means the universe draws the line, not our electronics." That line matters because the team runs the meanest test it can afford. Hold pointing steady. Keep DSN geometry as stable as schedules allow. Change internal spacecraft states and watch whether the pattern moves. If the pattern shifts with internal state, the instrument owns it. However, if the pattern stays fixed on the sky, space owns it. The ribs stay fixed enough to hurt everyone's feelings because now the universe carries the burden of explanation. So if the universe draws the line, what does the line separate? Two plasmas, two magnetic regimes, or two different kinds of space stitched together? Now you get to plant your flag, because this mystery only gets solved faster if people argue well. Comment seed number 1. If you control one last Voyager experiment, do you chase the 2600 Hz tone or chase the 02.17.43 tick source, and what outcome would change your mind? Comment seed number 2. If you design the next interstellar probe based on this, do you prioritize more power, more shielding, or more redundancy? And what do you sacrifice to afford it? Poll seed. Pick one explanation. A. Magnetic seam. B. Dust sheet. C. Turbulent ribs. And tell me the one prediction your pick makes that the other two can't. Voyager drifts alone, but it carries a mirror of us. math, music, and the golden record into a region that doesn't care, and that indifference makes every new signal feel like a personal message anyway. The spacecraft keeps moving, the power keeps shrinking, and the tones keep appearing like a code the universe writes at the boundary of the sun's influence. However, the loneliest part isn't the distance, it's the time. Every answer arrives 23 hours late, and every late answer might be the last one. So when Voyager finally goes quiet, do we lose a spacecraft? Or do we lose the only ear we have pressed against the wall of interstellar space? And what do we send next to touch that wall again?